Hi everyone. Today we'll look at two different concepts. First one, we'll take a look at roots of complex numbers, and then we'll look at graphical representation of complex numbers. All right, so let's get started with roots of complex numbers. Now, oftentimes what we'll have is we'll have something, we'll have z, and then we're going to be given, well, z can be represented in x plus iy form, right? So we're going to be asked to find the square root of z, or in simpler terms, we'll be requested to find square root of x plus iy, right? Now, how can we do this, right? So this square root of a complex number will actually result in another complex number. So let me write it here. Square root of a complex number will result in another complex numbers. In fact, you'll be getting pairs of complex numbers, right? Okay, so if we're supposed to find the square root of a complex number, say x plus iota y, right? And we'll actually get another complex number, right? Something like this. So where a and b are real numbers, right? This is key, right? Where a and b are real numbers. So the way we can evaluate this is, we have a square root here. So the only way we can get rid of a square root is by squaring both sides. So if we square both sides, what we have is x plus iy is equal to a plus iota b whole squared. And if we simplify this, we get x plus iota y is equal to a squared minus b squared plus, I'll write I to ab, right? Now, if you remember from the previous video, we talked about checking, comparing different real parts and imaginary parts, right? So if I change the color and if I make it pink, right? So this and this corresponds with each other. And then if I take line, y corresponds with 2ab. So if I rewrite this, we can say that x is equal to a squared minus b squared, and y is equal to 2ab, right? So essentially, we're going to look at this, and then we're going to get, we're going to get a squared and b squared, and then we can find x and y. Well, we're going to have x and y, and we're going to get a squared and b squared depending on the values, right? So let's look at an example now. So the example which I have is square root of 7 minus 24i, right? Let me change the color. So let's take aqua. So we have find the square root of 7 minus 24i, right? So before I start and give the solution, pause the video, try it on your own. I mean, see, the process remains the same, right? We have, this is our x, this is our iy, and based on that, we're going to have two equations, right? Now, what I can tell you is that you're going to have to make some substitutions here. You're going to have to get rid of certain variables and then bring in certain variables, right? You're going to have to get, so we're going to have x and y. X and y, obviously your numbers are given, right? You're going to have a and b, two variables. You're going to try to remove one of the variables by substituting b or substituting a, right? That's the hint I can give you. Now try to try to do it on your own. Pause the video and come back for the answer. All right, so let's get started. So we're told to find square root of 7 minus 24i, right? And it's equal to a plus iota b, right? Now if I can apply the shortcut method where the real part is equal to a squared minus b squared and the imaginary part is equal to 2ab, but I'll show all the steps just for the sake of clarity, right? I'm going to square both sides, so if I'm going to get 7 minus 24i is equal to a plus iota b whole squared. So then we're going to have 7 minus 24i is equal to a squared minus b squared plus iota 2ab, right? So I'm going to get a squared minus b squared is equal to 7, and 2ab is equal to minus 24, right? Don't forget the minus sign, right? It's because it's a plus I. Here it's a minus I, so we're going to take the minus with the 24, right? Like this, right? So this is the two conditions or the two equations that we have, right? So let's simplify this a bit. Let's simplify this equation. If we simplify this equation, what do we get? We get AB is equal to minus 12, okay? Now, like I said before, your job is, since you have two variables, your job is to eliminate one of them. And the way you can do that is simply by doing substitution. So let's get rid of b in the first equation. If we do that, we're going to have b is equal to minus 12 upon a, right? So let's go to the next page, right? So we're going to have a squared minus b squared is equal to 7. Then we have a squared, and for b, I'm going to put in minus 12 by a. So I'm going to have minus 12 by a whole squared is equal to 7, right? Then I'm going to have a squared minus 144 upon a squared up is equal to 7. Let's try to make it a quadratic formula or something like that, right? So I'm going to have to multiply by a squared on both sides. So if I multiply by a squared on both sides, what I'm going to have? I'm going to have a to the power 4 minus 144 is equal to 7a. Sorry, 7a squared. Then I'm going to have a to the power 4 minus 7a squared minus 144 is equal to 0. Now, this kind of looks like a quadratic equation, except the only difference here is that we have powers of 4 and 2. So we're going to do another small substitution here. The substitution that we're going to do, and I'm pretty sure you guys have seen questions like this, especially if you're done add maths in IGCSE program during grade 10 and 9. So you must have seen you must remember how we solve these types of questions, right? For those who haven't, let me just explain what I'm going to do here, right? I have a to the power 4 a squared, right? So I know how to work with quadratic where we have powers of 2 and 1, right? But we have power of 4 and 2. So the substitution that I'm going to make here is I'm going to write t is equal to a squared, right? So wherever I see a squared, I'm going to put t, right? So if I do that, what do I have? I'm going to get, well, I'll change the color again. Let's take purple, right? So with this information, I'm going to have a t squared here, right? Because it's a squared squared. So I'm going to have t squared minus 7t, minus 144 is equal to 0. Now we have our normal quadratic equation. So now if you can't, well, I can see the factors in this question. I can see the factors of 144 are 16 and 9, which will minus 16 plus 9 will give me a minus 7. Now, if you don't get it immediately, you can try quadratic equation, but that can be really lengthy, or just try to create multiple factors of 144. So, if it didn't, strike you immediately, you can try making factors like 1 and 144, 2, 7, 2, and so on and so forth until you come to 9 and 16. Then you'll know that minus 16 plus 9 will give you minus 7. So the factors here are actually t minus 16 and t minus 9 is equal to 0. Sorry, t plus 9, because I need a negative number, right? T plus 9. Hold on, let me rewrite it. So t plus 9 is equal to 0. So the values of t I'm going to get is t is equal to 16 and t is equal to minus 9. Now, we know that a squared was equal to t. So therefore, I'm going to change the color again now. So I'm going to change the color again, and I'm going to get a squared is equal to 16, and a squared is equal to minus 9. So now, if you remember from the condition that we had, a and b are always real numbers. Now, I've written somewhere here, a and b are always real numbers. They're not imaginary numbers, right? So technically, you could have written a is equal to plus minus 3i. But remember, a and b are real numbers. They're not imaginary numbers. So this scenario is not possible, right? So we're left with the scenario. So a is equal to plus or minus 4. Okay? Now, we have the value of 4. The value of a. Now we have to find the value of b. So we had one equation right here, right? B is equal to minus 12a. Let's bring that in here, right? So if a is equal to 4, b is equal to minus 3. And if a is equal to minus 4, b is equal to 3. So the two complex numbers, or the two roots that we have, are z1, I'll denote it as this way, is 4 minus 3i, and z2, which is equal to minus 4 plus 3i. So basically the square root of 7 minus 24i is equal to 4 minus 3i and minus 4 plus 3i. And the way you can check this is that you can square each root by itself, right? You can just square this root. So you can do minus 4 minus 3i into 4 minus 3i, and you can do minus 4 plus 3i times minus 4 plus 3i. When you square both of them, you'll get 7 times 7, sorry, 7 minus 24i. So this is a very streamlined process. Nothing too crazy. It's a very basic straightforward process. There's nothing new about it. Just have to follow this every time. You're gonna have two different variables, and then you're gonna have to make a substitution, like I did here, right? You're gonna have to make a substitution here. You're gonna have to make a substitution here, and then you're gonna have to simplify. You're gonna have a quadratic equation. After the quadratic equation, you're gonna have two possible values. Sometimes this can even, this could have been plus 9 as well. So you would have actually had four roots, but I don't think it will happen just because it's a square root. So then you had two possible values of a, and based on that you had two possible values of b, and thus you had two possible roots of the entire answer. So now that we've completed square roots of complex numbers, let's move down to representation of complex numbers, but this time graphically, right? This is something that's new, right? So the first thing that, I would like to refresh your memory before we start with all of this, right? So if you remember back in elementary school or early middle school, right? Sixth grade or fifth grade, we used to talk about number lines a lot, right? And number lines used to tell us what? They used to tell us where each number lies, right? How big is it? Whether it's bigger than the number, whether it's smaller than the number, or whatever, right? Whatever it may be. So now we have a number line. Now we know 1/2 lies somewhere here. We know that e lies somewhere here. Let me bring it a bit down, right? E lies somewhere here. We know pi lies somewhere here. Maybe minus 2.5 lies somewhere here, right? So this is like kind of like all the real numbers are in one number line, right? Where we can see which number is smaller than which number and which number is greater than which number, right? Now, what if we develop an imaginary line, right? This was for real numbers, right? For real numbers. But what about for imaginary numbers? Well, for imaginary numbers, nothing changes except the fact that we add an iota everywhere, right? Let me show it graphically, right? So again, I'm gonna make the same number line, right? Same number line. Put a 0 here, but instead of writing 1, I'm gonna write 1i or just I, right? 2i, 3i, right? And then minus I, minus 2i, and minus 3i. Right? Nothing changes, right? We know that 2i is greater than I, 3i is greater than 2i, minus I is greater than 2i, and minus 3i is less than I, right? Nothing changes. We follow the same process on imaginary numbers as well. Right. Now the situation rises. What if you want to represent, something, a complex number where we had z is equal to x plus iy? So in that, we kind of, mix both of these scales together. But this time, we put the imaginary scale on the y-axis and the real scale on the x-axis. So let's talk about the Argand plane. Now, the Argand plane consists of two axes, similar to what we've learned in middle school, right? The x-axis and y-axis. Nothing changes. Same principles being followed, right? But this time, the x-axis is called the real axis, where we have all the real parts of the complex number, right? Real numbers. And then we have y, where we have all the imaginary numbers. Right? So, now suppose let's take a few examples of random complex numbers, right? So if we have z1, let me change the color again. So if we have z1, maybe we have 3 plus 2i, right? So before that, yeah, z1 is equal to 3 plus 2i, right? So how would we, plot that on the Argand plane? Well, before, let me just set up a bit of units here as well. So if we create spaces, so we have 1, 2, 3, 4, 5, right? Similarly, we have 1, 2, 3, 4, 5, right? And then so on and so forth. -1, -2, -5, -1, 2, -5, right? So if you have to plot this, right, how do we do it? Well, we know it's 3 on the real axis. So we go 1, 2, 3, and then 2 on the imaginary axis. So exactly right here. So we'd have Z1 right here. Right? Again, let's take another one. -2 minus 3i, right? So if you take Z2 as -2 minus 3i. Well, on the real axis, we go -2, so 2 to the left, right? So maybe 1, 2, and then 3 down. So 1, 2, 3, somewhere here. So we'd have our Z2 right here, right? So essentially, we're plotting it exactly like the way we do for normal coordinates, right? Technically, so if we're given the complex number z is equal to a plus iota b, on the Argand plane, we're just plotting a comma b, right? Where this is the x component and this is the y component, right? Nothing changes. So if I have to generalize this, right? So I can just, generally just make a dotted line here and then something like this. And I can put a circle here, put a dot here, and I can say z and a comma b, right? That's it. I can just end it right here. I don't need to, I can generalize in this way and I don't need to, complicate it at all. So again, uh, complex numbers are drawn on Argand plane very much like you do normal coordinates, right? The the I component or the imaginary component goes on the y-axis, real component goes on the x-axis, right? Now, let's talk about the Cartesian form. So the Cartesian form is just a really fancy way of representing a points on a Cartesian plane, right? The Cartesian plane is nothing but x and y, right? So essentially, what we're doing is Cartesian form is z is equal to x plus iy. Now, every time you see something like written in the x plus iy form, a complex number, it's written in the Cartesian form. That's it. That's all you need to know about. And its points are x comma y, right? That's all that this Cartesian form says, right? Now the reason why we say Cartesian form is because as we move forward in complex numbers, we'll get to a concept called polar form, right? We're going to talk about Euler's method and everything. We're going to have to where we're actually going to represent complex numbers not by the x coordinate and y coordinate, but by its modulus and its angle subtended from the positive real axis, right? So that's the reason why we specify that yes, we have a Cartesian form or we don't, right? So you might be thinking, what's the need of saying something like Cartesian? Why don't we just say normal normal plotting or normal method, right? We're trying to differentiate because there's more than one method, right? Now, again, before we move forward, one more thing that I want to mention is kind of important. So if I draw an Argand plane right here, right? So we have the imaginary axis on the y and the real on the x, right? So imaginary and real, right? So this is my origin. Now if I have 2 points, right? Suppose point z1 here and z2 here, right? So if I have those 2 points, just note that you can't decide which point is bigger, right? Complex numbers are just they're just representing points on the Argand plane. They're not telling which one is bigger. So you can't compare Z2 and Z1 in terms of size. Okay, so let me just make a note here, right? Note, or I'll just make it a little bit further down. So then what I want you guys to remember is this is just all conceptual knowledge, right? Just so you guys are aware, so you guys don't, when you guys are preparing or practicing, you guys are never confused of what's actually being asked and what you're actually writing. So since complex numbers are representing points in an Argand plane, right? Are representing points in an Argand plane. They cannot be compared. They cannot be compared to check which one is bigger, right? All they're doing is they're just representing the location of each complex number. They're not telling that you cannot compare size um, of each of one another, right? So compared to check which one is bigger. However, we can compare one thing, right? And if if you guys have already learned this in class, you can compare the modulus of the complex number, right? The modulus. So for those of you who don't know, that's not a problem. I'll be talking about modulus right now. So that's the first property of graphing of which I want to talk about today, right? So the first property is number one is modulus. In simple terms, modulus is the distance from the origin. From the origin. That's it. So now, if I have an Argand plane, again, all of my concepts, all the properties that I'm going to discuss today are going to be, done via a Argand plane because that's the whole idea. So if I have a point right here, right, its coordinates are obviously x comma y, right? So now I'm going to have, this is its distance, right? This is its distance. So this is the modulus, right? So this is my modulus, right? So, and this is, hold up. So this dotted line right here, the vertical dotted line, will be my y component, right? Because it's y units above from 0. And this part will be x, right? So it's x units away from the origin, right? So now if you remember, right, your triangle properties, you'll notice that this is a right triangle being made here, right? Because it's directly down, it's perpendicular to this horizontal line. So what we can do is to find the modulus, we can simply apply the Pythagorean theorem, right? Which basically says a squared plus b squared is equal to c squared, right? Where c is the hypotenuse, so the hypotenuse, which is the modulus in this case, is simply a squared plus b squared, right? So if we actually have to find this distance, right? If I name this O for origin and P for the point, right? The distance OP is equal to the modulus, which is x squared plus y squared, right? That's all, right? So now if I have to explain it in complete mathematical terms, right? So modulus is always represented like this, right? Like the absolute value sign to use. So modulus is like this. So if we have z is equal to x plus iy, modulus of z is equal to x squared plus y squared, where we do square of the real part, square of the imaginary part, add them, and then define the square root again, right? That is all what the modulus says. Now, just one more note. If you remember, like absolute value from the number line, right? Moduluses are always positive because they're the distance, right? Distances are always positive, they're never negative. Just one more note that I want to make here is that even though we have a square root, right? A square root of any real number, you can basically have plus or minus, right? But notice the absolute value sign here. What does the absolute value sign always say? That the number, that the answer, or whatever it is always positive, right? And just note that the modulus of any complex number will always be positive, right? Because what modulus is essentially, is telling us that it's a distance from the origin. And what we remember, or if you know, distance is always positive, right? Distance can never be negative. So just note that if you get, if you get like, square root of 9 as your modulus, and then you say, oh, it's plus minus 3. Now I don't know which one to take. No. So you always remember that you have to take the positive one. Never take the negative one because it's a distance, and distance is always positive. So now let's look at the second property, which is the conjugate. The conjugate, simply by mathematical terms, is the image in x-axis, right? So let's draw this. Let's explain this via Argand plane again. So if I draw a plane, like this, right? So I'm going to have maybe a point somewhere here. I'm going to name it Z. And then now, if this is the x-axis, right, and I want the image in x-axis, so the image of the point will lie maybe somewhere here, approximately here, right? So how do I denote a conjugate, right? Conjugate is always denoted by basically conjugate of Z is denoted by Z with a bar on the top. So every time you see a bar on the top of a complex number, you know that it's a conjugate of the complex number. So this would be denoted as Z bar, like this, right? So now let me just tell you some things about the complex or about the conjugate, right? So first things first, the modulus of both a complex number and its conjugate is the same. So mod Z and modulus of Z bar, right? So modulus of Z is equal to modulus of Z bar. And the simple reason is that their x component and y component are the same in magnitude. They only differ in signs, right? So if I have Z is equal to x plus iy, Z bar will be x minus iy, right? And in the end, see, if you remember, modulus is nothing but square root of the real part and the imaginary part. So similarly, modulus of Z bar will be x squared plus y squared, right? X squared plus actually be minus y whole squared, which will result in y squared only. So this is why both modulus are the same, right? So this was conjugates, and I know oftentimes you guys might have been confused because I introduced a question with conjugates in the previous videos, and since I didn't explain it, now I'm explaining it properly. And one more thing I want to mention is, if you guys haven't seen my previous video, if if a complex number, if z is equal to x minus iy, then its conjugate will not be x minus iy. It will be x plus iy. Just know that oftentimes, people get confused because if they get confused, they're like, oh, there's a minus sign here. So if we start with the minus sign, will we still have a minus sign, or will we have a positive sign? Yeah, so yes, the sign changes every time in the conjugate of the imaginary part. Just note that, because technically, think about it. We're talking about the image in x-axis. So if this is our z, right? If this is our, let me change the color of laser, right? So if this is our z, right, and we want its image, exact image, so it would be right here, right? If its image is right here, it's gonna have the sign. The x component will be the same, but the sign of the y component will change because it's on the opposite direction, right, from the x-axis. So this is why we have the sign change for the conjugates, right? Okay, so now let's do a simple, quick example. So if we're given that z is equal to 5 minus 12i. Sorry, my bad. Let's make it a little bit more confusing. So if we're given that z is equal to minus 5 minus 12i, so we're going to have to find part A, find its conjugate. So find z bar, conjugate z bar, and B, find modulus, right? So how do we find its conjugate? Well, we know that if z is equal to x plus iy, z bar is equal to x minus I. Basically, the real x, the sign of x remains the same, but the sign of y changes. So we have z is equal to minus 5 minus 12i. Now, if we want z bar, the conjugate, all we have to do is just change the sign of the imaginary part, and we'll have plus 12i. So this is conjugate. Now we have to find the modulus. Now remember, if you find the modulus of this or this, doesn't matter. We're going to get the same value, right? Modulus is the positive distance from the origin. Whether it's from z or whether it's from z bar, doesn't matter, right? Because again, magnitude of each component, each real part and imaginary part is the same. So modulus of z, if we go to find, is nothing but x squared plus y squared. So we know x is equal to minus 5. Let's take normal z. So we're going to have minus 5 whole squared plus minus 12 whole squared. So this gives us 25 plus 144. which gives us 169, which is square root of 13. And if you're wondering how I did it so quickly, no, I did not have the answers next to me. I know this because it's the 5, 12, 13 is a Pythagorean triple, and that's why I know if 5 and 12 are the legs, 13 will be the hypotenuse. If you didn't get it, don't worry, ignore what I just said. I just said it, I just used this example as a 5 and 12 because the numbers are going to come out to be really nice and easy. Forget that. The whole key out of this is just I just want to get you in the habit of basically understanding the conjugate and finding its modulus, right? So it's quite simple, nothing too crazy, and that's exactly what you're gonna have to do in the exam. Like they're not gonna ask you some crazy stuff. They're gonna ask you very simple things, right? Obviously they're gonna be a step higher because there will be multiple concepts embedded into one question. So this is all for today's video. I just wanted to give you guys a brief conceptual knowledge of what graphical representation looks like with complex numbers. Like I said, it's quite simple. It's kind of the way you work with your normal graphs with real numbers only, right? So in the next video, what we'll do is we'll take a deeper look, or we'll actually start with polar form. We'll talk about modulus. We'll talk about argument and how Euler's form was derived, and we'll look at all that. Now, for those who haven't started trigonometry yet, I would recommend that you skip the next video simply because the next video will focus highly on will be solely based on trigonometry. And if you haven't thoroughly revised your trigonometry, you will be very confused of when I'm finding the argument of different complex numbers, why it's going negative angle, why it's in the positive angle, why tangent is being taken in the positive as third in the third quadrant, and all those sorts of things, right? But once you revise your trigonometry, or once I upload videos on trigonometry, once I upload those tutorial videos, you can take a look at those trigonometry videos and then come back to the next complex number video that I'm going to make, right? Otherwise, if you have already if you're using if you're using these videos as a revision and you've already learned your trigonometry and everything, so you can go ahead and watch the next video, no issues. Again, I'll make a point, I'll mention this before when I start the next video again, so you don't waste your time. You're gonna make your head's gonna spin around for the whole time, even if you try understanding it. So I just recommend don't watch the next video if you haven't revised your trigonometry at all, right? So this was all for today's video, and I'll see you in the next one. Bye bye.